Yeah, I was going to do a little intro, but it seems like you already kind of know everyone here in some form. But people who don't know Tom, I suppose we best know him through all of his work on Opali, which is the kind of foundation we've got underneath Relate. But he does a lot more than that as well. I see you're also on the Haskell Foundation and also super active on the Core Libraries Committee, which is also very, very cool. And yeah, talking today to us about Bluefin, which is his new effect library. So welcome, Tom. Thanks for this, and I'll hand it over to you.
Thanks, Ollie. Well, really good to be talking to CircuitHub today, a company I've followed for a long time, and talking to friends old and new. And yeah, I'm going to be talking about Bluefin. And that is because I believe Bluefin is the future of Haskell. Bluefin is an effect system. So it's like transformers and MTL or polysemi, effectful in that regard. In fact, Bluefin is very similar to effectful. It's very strongly based on effectful with a slight difference, which I believe really makes a huge ergonomic improvement. So I'm going to tell you a little bit about what that difference is and why I think it's so beneficial. Actually, most of the talk today I'm going to be spending talking about the background of IO-based effect systems, which effectful and Bluefin are, and why they're necessary in the context of the history of Haskell. And hopefully that sets the scene for why effectful and Bluefin are necessary, and helps you to more easily understand the difference between Bluefin and effectful, and what the ergonomic trade-off is there. So in this talk, I'm going to take the existence of monads for granted. If you go back 30 years in the Haskell world, then monads didn't exist. We didn't have this notion. It was introduced as a fresh notion into the pure functional programming world as a way of dealing with the semantics of effects. But now that's established. So I'm going to take that for granted and just talk about effect systems which use monads in the way that they express effects in programs, and that is the one way that you will find effects done in Haskell. And I'd like to talk about what the properties of effect systems are and a little bit of the historical background. So what we really want effect systems for is to be able to use things in our program like state, mutable state, the ability to throw exceptions, the ability to do general I/O, print to the terminal, open network connections, interact with the disk, interact with any hardware in the operating system. And there are a few different properties of effect systems that are beneficial that I've listed here. So one I call encapsulation. That is the type of the value in your program which reflects an effectful operation, tells you where you don't do effects, actually. That's quite useful. If you think of something like the IO monad, which is a sort of effect system, it introduces the ability to talk about operations which do IO, but sort of by definition, it means that anything that's not tagged with this IO type doesn't do IO. So you have a form of encapsulation. But what you don't have is the ability to do fine-grained encapsulation of effects. So if you're in the IO monad in Haskell, you're just in IO. You can do arbitrary states with IO refs. You can throw arbitrary exceptions. And of course, you can do arbitrary IO operations. So you don't have fine-grained effects. Another property we might want of effect systems is called resource safety. If you're accessing some resource that's, well, either outside or inside your program, but typically outside, like database connections, file handles, these are scarce resources. We don't want to hold on to a resource for longer than we're using it. So one property we want is don't free a resource too long after we stop using it. Give it back to the operating system. It can be reused, recycled in other programs on your system and so on. You also don't want to free a resource before you stop using it because you're still using it. Your program's going to go wrong if you close a file handle and then try to read from it afterwards. Another property we want is predictable performance. So being able to look and make a reasonable assessment of performance properties of effectful code from the structure of the code right in front of you. So let's have a look at how IO does that. Well, it has encapsulation of a sort, but not a very good one. So I'm going to give it an X for that. For example, you can throw and handle exceptions, but if you throw an exception and you handle the exception, you don't see in the type of the IO action that the exception is not observable from the outside. You've caught it, so it can't propagate further, but nothing reflects that in the IO type. It's not fine-grained. You can do your mutable state with IO refs, you can throw exceptions, you can do any arbitrary IO interacting with the Haskell runtime system or the operating system. There's no distinction, it's just all IO. On the other hand, it does have resource safety and it does have predictable performance. It has resource safety because you have, for example, these things called bracketing operations. Here's the definition of with file, which is not quite the definition in base, but very similar to it. You can open a file, and that gives you access to a file handle, which you then use in the body. The body is this argument here that takes a handle and runs an arbitrary IO action. And once the body's finished running, then you close the file. And this close file runs even if the body throws an exception and we leave the bracket through abnormal termination. It means that even if you throw an exception, this cleanup will happen, the file handle will be returned to the OS, and that's great because file handles are a scarce resource. So IO wins in that regard. It also has predictable for performance in the sense that the IO monads, you read through a list of instructions, they're happening one after the other, or a list of actions written in, say, do notation, they're happening one after the other, and there's no sort of hidden behaviors that are not sort of directly obvious in the structure of the program. You can still write complicated programs, but if you look at how the program is implemented, there's no sort of long-range action at a distance, which can introduce hard to analyze performance characteristics. Now, IO is not the only way to structure programs, and people did want this sort of fine-grained encapsulation kind of thing. So an early developed approach was building effects out of algebraic data types. So modeling effects as data, basically. This is often called the transformers approach. That's the approach taken by the transformers library in Haskell. So instead of exceptions being something built into the runtime system, they're data. If I want to model the ability to throw an exception of type E, in a monad M, then I run an M action, and I can either fail with the exception of type E, or I terminate normally with the result type A. Same for state. You model state manipulation as pure data. The state transformer here takes an initial state type S as an argument to a function, does an M action, and returns the final value of the state type S, as well as the termination value A. And you can mix these together. So if I want something that has exception state and IO, I stack my monad transformers together, and I ultimately get something that takes a state S, does some IO, and finishes with either an exception type E or a normal result type A, and the new type of state at the end. So that's great for encapsulation and for fine-grained effects. If I have something that throws an exception on the outside of my stack, then I can handle that exception with run except T. I get an either out, I can do whatever I like based on that either. And in the final type, I no longer see exception in the type, no except T there. So the exception is handled, and it's not observable from outside this function that there was any exception in there at all. It's all encapsulated. Unfortunately, this leads to poor performance because modeling things with ADTs that are actually supposed to be functions code can be pretty slow unless GHC can optimize that really well, which sometimes it does well, particularly within modules, and sometimes it does badly, particularly between modules. And doing resource safety for this transformers approach in general was very hard. And I won't go into more details about the history of that, because that's also quite a long history, but it's been difficult. So we have this sort of dual trade-off. The pure I/O approach is great for resource safety and performance, but it's bad for encapsulation. There's no fine-grained control there over effects. Transformers, and also later effect systems like polysemi, fused effects, and so on, which are based on similar sort of ideas of building up computations, representing computations as ADTs, have the opposite. You get great encapsulation and fine-grained tracking of effects, but no resource safety, no predictable performance. So a few years ago now, Michael Snoeman said, let's just use I/O. It's far more important in practical programs to have resource safety and to have predictable performance. And if you just use I/O, then you're either restricted to passing around handles and even, I suppose, I/O refs and so on for doing mutable state, say a file handle and a database handle, passing them around by hand. Or Michael promoted this reader TIO pattern where you stick your handles in some sort of app type and you just pass that around implicitly in a reader T. So the reader T monad is passing around the app type implicitly. You don't need to pass it yourself as an argument, but it's in the environment of your program. And this works really well to achieve those aims, to achieve resource safety and to achieve predictable performance. But I found it really quite disappointing that we didn't have encapsulation. We didn't have this fine-grained tracking of effects. And that was really the case until Andrzej Rubczak a few years ago released effectful, which I found really groundbreaking, actually. I think it was a great idea of getting the best of both worlds. Let's use I/O and also provide encapsulation by defining a monad that is basically just I/O under the hood. It's called EFF, but using the type system to track which effects can happen at the type level. So this foo here can do an error effect, which is basically an exception, and can manipulate mutable state. That's what it says in the type system. And then if you handle the error effect with this run error no call stack, well, then you no longer see it in the type. So there can be no way that the exception thrown by foo within bar can be seen from the outside. And that's indeed what the type of bar says. It says the only effect you can see from the outside is the state effect. So this really gets the best of both worlds, and I think is a great innovation in the Haskell world. Bluefin, by contrast, is a small difference to effectful. And the difference is that instead of passing instead of tracking effects at the type level as constraints, I developed Bluefin so that you pass in effects as value level arguments. So this exception thing here is not just a constraint saying that foo can throw an exception. It is actually a value that you pass in to give the ability to throw an exception. And this state here is not a type level thing just saying it does manipulate the state of type S. It is actually a reference type like an I/O ref that you pass in and you can manipulate yourself. And this is a slight difference to effectful in terms of the overall 30,000 foot view of the thing. But I think this makes a big difference to ergonomics, and I think it allows you to write much more complicated stateful programs whilst maintaining a good degree of control or understanding over them. Because you have these explicit signs of where effects are happening as value level arguments, that makes it a lot easier to deal with the complexity that arises when writing more complicated effectful programs. or programs that use effects. So just to compare what happens in the Bluefin case to the previous effectful case, the difference is that we have this exception handle brought into scope by try, which is equivalent to the effectful run error, and we pass the exception as a handle to foo, and we have a state reference which is passed into bar, and we also pass it into foo so that foo can manipulate that state. Those are the differences, really. So I'll talk a little bit in a moment about what the ergonomic differences are here, but let's just sort of recap and summarize. And by the way, please do raise your hands, ask any questions, make any points if you want. If there's something on your mind, feel free to just chime in. So this is a little comparison of what effectful types versus Bluefin types look like. In both cases, it's the type of some operation that can raise an error or exception of type E and also manipulate a state of type S. In the effectful world, you pass in these things as, well, implicitly as constraints. So they got the double fat arrow. And the monad in question in both cases is called EFF, and there's a sort of effect tag thing, ease, in both cases, and they differ in how the effect relates to that E thing. Here we say that error E kind of belongs to ease and state S belongs to ease. Bluefin, it's slightly different. You have a single arrow, so a normal function arrow, because this error thing is a value level argument. It's just a normal argument. In fact, in Bluefin, this is called exception, not error, but I've called it error here just to try and make the correspondence easier to see. So in both cases, we pass in error and state as normal value arguments with a normal arrow. We also have this ease, and we have these effect tags on the handles E1 and E2. And the relationship between E1, E2, and ease is actually passed at the constraint level, the type level, but it's slightly different in that it sort of doesn't have any content. There is there are no methods associated with this type class and so on. It's just a property of E1 and E2. So there's no complexity in this. In these constraints, there's no sort of behavior in them. It is just sort of tying them together and saying they belong together. Whereas these constraints really do something. They make something available in the body of the effectful operation. So in summary, we have these two worlds we saw initially, the IO world that has some benefits, and the transformers / polysemi / fused effects world, which has the complementary benefits. MJ's idea was, actually, let's get the best of both worlds. And Bluefin follows that. So we do have encapsulation and fine-grained effects. We can track effects at a fine-grained level, individual exceptions, individual states. And we can handle effects and remove them from the type. So that's great. But we don't give up resource safety. We don't give up predictable performance, because everything is just IO under the hood. So we get all the benefits of IO also. There's one thing that you do give up, notably, which I haven't actually written down, but you do give up the ability to use effects that are what are called multi-shot continuations. So these would be kind of logic T or search effects, backtracking effects, where you can explore certain code paths and then unwind them, go back to an earlier stage of computation, and continue from that earlier stage of computation. You give up these kind of things. And I think that's a great trade-off, because although they're useful in some cases, they're not useful in the vast majority of programs. And you can still obtain them in effectful and Bluefin by using something like a logic T transformer on top of effectful or Bluefin's F monads. So you're not giving up that much in that regard. Now, notably, this doesn't include coroutines. So it doesn't include streaming effects like pipes, conduits, streaming, those Haskell libraries. They can still be represented in Bluefin, and they can still be represented in effectful, actually, but effectful doesn't have them natively in its basic libraries, but there's no technical reason it couldn't. So I think those are great things to have at your fingertips when writing real-world code. So we can sort of divide a matrix into 4 pieces like this. We have the fine-grained encapsulated world, and we have the world that doesn't do those encapsulation effects. We also have the type-level environment world where things are passed implicitly, and the value-level argument world where things are passed explicitly. So Bluefin sits here in the fine-grained world where you pass things as value-level arguments. It's a bit like a typed version of just plain I/O. And effectful, you pass things implicitly, and that's a bit like a typed, well-typed version of the reader TIO pattern. So before we dive in to look at any Bluefin specific stuff, has anyone got any questions, any thoughts they want to share?
I guess the thing I wonder a bit about I'll maybe have some more questions about later with Bluefin. So going back to your comparison with effectful, you need both a constraint and a value argument for every effect. Is that right?
Yeah, that's right. So you'll always have this pattern in Bluefin. You'll have a value level argument, and then you'll have this constraint that ties the tag of the value level argument to the tag of the F mode.
Mm-hmm.
Yeah.
Mm-hmm.
So it's always exactly this pattern.
And that's presumably kind of essential. Like, is it possible to do it with just one or the other, or do you kind of need both?
It doesn't
doing
seem...
just the constraint is effectful, right?
Yes, that's right. If you do it, so in technical terms, these are empty type classes. They don't contain any methods and they don't contain any runtime data. Whereas effectful ones do contain runtime data. These really contain some references to places in the F monad where effects have been stored, or the ability to do effects has been stored. So in a sense you can't get these wrong in Bluefin. The compiler will tell you when you don't have one, and you just have to go and dutifully add it. But it does have to be there. What you can get wrong is you can pass the wrong effect. So these kind of crop up naturally as a consequence of just using effects. But they also do have to be there to ensure that the type safety properties of the implementation of Bluefin go through.
Did you have something like, I'm imagining I could write a wrapper around error E1, which is error E1 E's, which is just an error, but also packages up the E as a member of E's dictionary or something.
Yeah, you can do that, and that would be isomorphic, but it turns out not to play very well with with how you remove effects in handlers. It's a little bit subtle, and it's sort of, in a sense, it's a sort of coincidence that it works. What we're doing here is we're encoding a set type, essentially. Rather than this E's, if we had a set type, I don't mean like a type level set type, I could just put E1 union E2 here instead of E's. That's what I'd really want to do. I want to say that the effects that occur in F are no less than the union of the effects of error and the effects of state. But we don't have a type level set in Haskell. So we encode it like this, and it works pretty effectively. It's these extra constraints are a bit annoying, but they are mechanical. So so it tends not to be too big of a deal.
I just had a question on kind of related to your point about using logic T, and you can put logic T on the outside of kind of effectful and Bluefin. What you can't do with that is put it right deep on the inside, which is significant sometimes, because it kind of means, do all of my search leaves have the same state, or every time I fork, do I get to kind of duplicate the state? Is that something that is possible here? If you had like F change to kind of like FT and take a base monad? So I know you'd give up the resource safety, but I'm wondering, because you've got encapsulation, if you can only guarantee resource safety with a kind of resource effect. So I can't do kind of resource safe operations when I change my base monad out of IO, but maybe I don't actually care about that in whatever I'm doing.
This is a tricky question in general. It has many different strands to it. So I don't think there's really a satisfactory answer. It's sort of a whole talk on its own, or maybe even more. It's also hard to define what you mean by resource safety in a world where you have multi-shot continuations, because if you acquire a resource during the capturing of a continuation, what do you do when you rerun it the next time? Do you acquire it again? Do you use the same one that already existed? It's really quite ambiguous, and so that is a very hairy area that I know enough about that I want to avoid it and not address it, but I don't know enough about to kind of explain in any detail all of the considerations.
You've got the ability to kind of grow your set of effects, but I kind of wonder if there's a kind of other side to that, which is kind of, I've got a set of effects that definitely can't contain resource using effects, right? So if we've got this question of what do you do with resources that you've acquired, you could also say, well, the moment you have a multi-shot continuation type base monad, I'm not going to let you do those things at all.
Yeah.
I'm just wondering, I don't know.
In theory, I think this is possible, and there's a very new library called Heftier Effects, which does take this approach. If you use IO and sort of resource stuff anywhere, or at least in particular places, then you can't use non-determinism. It just won't let you in the type system. So I think that is a plausible way of doing things. I think that might work, but there are still a lot of unanswered questions, and there's basically a focus on not doing that, because I think the returns to doing that are quite small, whereas the returns to supporting everything else are very large. So it's a sort of bet that doing it one way is going to be more impactful than doing it the other way. But there are definitely interesting questions to resolve in that direction.
Cool. I just have one more as well, which is on transformers. You kind of mentioned the state T on top of accept T. And as we know, you can also flip those around and you change the kind of runtime semantics of the program. Is that something that you can do in Bluefin, or do you kind of statically commit to a single execution? I mean, I guess you have to here, because these are just value level effect things.
Yeah, these are value level. So there's nothing stopping you just writing another function that would swap the ordering of these two. So we can't even in Bluefin stop you from doing that. Really, in the transformers world, it's not so much the ordering of the transformers that matters. I mean, it does in a sense, but I prefer to think of it as the ordering of the handlers that matters. If you handle the exception first, sort of more deeply nested, then at the time you're handling the exception, you've already got a state in scope. So your state continues to exist after you handle the exception. If you flip state and accept around, you have to handle state more deeply. So it means that if you throw an exception and you bubble up all the way up to the exception handler, the state is gone, because you only created it after you installed your exception handler. So I prefer to think of it in terms of the ordering in which you impose handlers, and Bluefin, like effectful, just says you can install those handlers in whichever way you want. So let's have a quick look at a Bluefin example. This I call safe lookup. Takes a list and an index in the list, and it returns you the value at that index if it exists. But if the list ran out, It's just going to return you nothing. So this uses an early return effect, which is basically an exception. Early return is saying, well, I've got my value now. Let's throw an exception with that value and bubble back up to the top. And it uses a state effect. So we use it with early return handler, so that when we return using this ret, we'll come back out of the with early return. That will be our final value. And in the state, we're starting with initial value n. We're starting a countdown. And when we get down to 0, we know we're at the correct element that we wanted to return. So we set up a loop. We iterate through these A's in the list. So for each X in the list X's, what we're going to do is we're going to get the countdown, put it in countdown prime. If that's 0, well, we're there. We're where we wanted to be. So now I'm going to return early with just X. That's the value we wanted. And if we're not at countdown 0 yet, then I'm going to modify the countdown by subtracting 1. And I'm just going to go round to the next iteration of the loop. If I fall off the end of the loop, then I haven't found it. So just pure nothing, returning nothing from the final result. And what is the sort of Bluefin special thing here? It's that we have these named handles, these named effects that refer to specific handlers in the program. So ret, this one allows me to return early. I only use it here. I can see, just by searching for ret in the program, all of the possible early return points. It's not to do with the type. If you are in the effectful world, if you're in the polysemi world, if you're in the transformers world, well, actually, maybe I should say MTL world, because transformers is normally when you're talking about concrete monad stacks. So let's say MTL, polysemi, effectful. You don't know where an effect is used just by looking syntactically at the code. You have to know the type of something. You would have to know that return early has a type that can use early return. Same with countdown. If I want to know which bits of the code modify the state, then I just look for where countdown is used. Same as I'm doing anything in Haskell. If I want to know where a particular value has influence over a particular part of the code, I just look for occurrences of that value. That is the wonderful benefit of pure functional programming. Same here. If I want to know how the countdown state can modify the behavior of the program or change the behavior of the program, I just look for where it's used. So this is very nice. I know that it can only be used in 2 places. So the mutable state can only have effects in 2 possible places in this code. So by contrast, effectful would look like this. Doesn't quite have a with early return, but it has something equivalent. I've just got a get. I don't know what type that get is. There's only one there's only one state in scope, so I guess it must be this one, which is an int. But if it's something more complicated, you could have 2 states in scope of different types, and you're not sure which one this is. I haven't got any non-Bluefin primitives here, but I could have some other function f of some other arguments. Does that use the state? I don't know. I would need to know the type of f to know that. Does it use an early return effect? I don't know. I need to know the type of f to know that. I can't see just from the source code that f is or is not using the state or the early return. So this really is the sort of the nub of the difference between effectful and Bluefin. In fact, I would say the fact that you have these arguments is the nub of the difference. And this is one of the consequences. In effectful, you can't see, just from looking at the code, without investigating the types of things, where effects can possibly influence the behavior of your program. There's also another thing, another aspect, which is simplicity. Here's effectful's type definition. I told you it's based on I/O. That's how we get the nice properties of resource safety and predictable performance. It also has this environment in scope that it uses to do its keep track of effects and what they should do. This is quite complicated. The environment is these three things, including a storage. The storage is very complicated. It's these 5 things: mutable prim array, small mutable array, and so on. And this is just Bluefin. It's a new type around I/O. That's it. That's all it is. So Bluefin is much simpler in this regard. Now, in a sense, I don't think it matters that much that effectful has some complicated internals, because, say, GHC has complicated internals, but presents a very nice interface to the Haskell programmer. So I don't think it's just a question of whether the internals are complex or not. One could learn to understand this effectful stuff, I'm sure. Don't think that would be an impediment. It's more to do with conceptual simplicity. The semantics of some operation are in Bluefin. Well, they are just what you'd expect from passing a handle into a function, into an I/O function. You have a handle that has an IOREF in it, or the ability to throw an exception in it, or a database handle in it, or so on and so forth. And then the function can use that to access the database, to manipulate the state, to throw the exception to the handler. So there's no confusion about what the semantics are of passing things at the type level. It really is just passing around values at the value level, and we understand what that means. We know when values can affect the behavior of a program. It's also conceptually simple in terms of creating new effects. How do I create new effects in Haskell, in Bluefin? It's just by making new Haskell data types. Effects are Haskell data types. New effects are new Haskell data types. If I want to make a new counter effect that allows me to increment a counter or have arbitrary access to the here's increment the counter. Here's throw an exception, say if I incremented it by too big a value, and here's a stream that can yield some diagnostic messages, for example. If I want those effects, those 3 effects, all I have to do is I have to define a data type that has those 3 things in it. That's very direct, it's very straightforward, it's just normal Haskell. This is what I call making compound effects. You can look here in the Bluefin documentation for the explanation of how we do this. I'll send the slides around afterwards and put a link in the chat here so everyone has access to that, so you can look at the links. But it really is conceptually simple in that regard. If you want to package some effects together to make a bigger effect, you just package them together in the same way that we're used to in Haskell. There's another reason. That is, Bluefin takes streaming seriously. And I think streaming is an extremely useful and very much underappreciated programming technique. It's used famously in the Haskell world in conduits, in the pipes library, in the streaming library. And these libraries are known and loved by their adherents. But I think even so, streaming in general should be more used in the Haskell world. It's just an astonishingly powerful tool. Now, what I'm about to say is not kind of impossible for effectful, because at the end of the day, effectful and Bluefin are built on the same idea, and what you can do in one, you can essentially do in the other, with caveats that I'll bring up. So you could do this in effectful, but it's not built into the base library of effectful. And there are also some other reasons why it's tricky. But let's have a look at how this looks in Bluefin. So I have this stream handle that I pass in. The stream handle is called Y, and it allows me to yield stuff to the stream. So like in the streaming library or the pipes library, you might yield something that sort of puts something on the stream. Here I'm yielding this message. Here's an example onto the stream. And then I have some function that I called yield some lines that can yield stuff to that stream as well, or it can throw an exception. In Bluefin, you can just wrap a try around that. You can catch the exception, and then you can continue on. If you don't have a streaming effect built into your effect system, then you have to layer one on top, say with stream T, pipes T, conduit T. And this is very similar to what Ollie's question was referring to afterwards. Once you put that on top, you can no longer use the effect library effects. You can't add them on top even more. So I wouldn't, if I was trying to write stream some lines, or well, let's say I was trying to write this whole block, instead of in effectful stream, I was just going to do stream T from the streaming library. I couldn't do this. I couldn't handle a Bluefin exception within a stream T block. For the same reason Ollie mentioned, you can't use sort of effectful or Bluefin effects on top of a logic T block. So you really need streams built in to your...
When you say built in, do you mean like built in, or do you just mean there needs to be an effect defined? Because I thought I saw you had some discussion on the effectful issue tracker that you could define.
Oh, yeah, that's right. When I say built in, I mean for the effect system. I mean not layered on top with a transformer.
Right, but in effectful, you can just define the thing. It's just that it's
Correct.
not been exported from effectful core or whatever.
Yeah, yeah.
Okay, right.
It doesn't need to even be exported from effectful core. Anyone could add a streaming effect to effectful, but it needs to be in the effect library and used to get the benefit of it. Yeah, you can't layer a transformer on top and expect to get the same benefit. So really what I'm saying is that using streaming pipes conduit on top of effectful or on top of Bluefin is not really that useful. You want to use an effect, a stream effect that's native to those libraries. There is another issue that don't really have a slide to explain this. Let's summarize these pluses for each of the libraries, and then I'll try to explain it. So with Bluefin, type inference is better because you're passing a value level thing around. You don't have to infer some constraints and get stuck in all sorts of ambiguous type errors. This is very related to the next issue, which is the one that I want to highlight, which is in Bluefin, you can have multiple effects of the same type in scope. You can have 2 integer effects in scope. You can have 2 string streams in scope.
I mean, you could do that with effectful's labeled effects, can't you?
You can, yes, that's right. But you can achieve the same end, but you can't do it in the same way. That's right. In Bluefin, you can literally have multiple effects of the same type in scope. I can have 2 stream strings effects in scope. I don't have to label one of them or new type one of them. They are literally both of type stream string. And I might want to have one that's logging at the top level of my program, logging everything, and another that's writing to a file and I'm handling it much lower down in a deeply nested call. So it's genuinely very useful to be able to do that kind of stuff. And I don't have to jump through any hoops to somehow distinguish them from each other. It might also be useful to do that. It might be useful to distinguish them so we don't get confused, but I don't feel it should be forced upon us. And effectful forces it upon us. Similarly, you can see where effects are happening. As I mentioned before, you just look at where a a handle is passed to know where the handle can be used. You don't have to know the type of anything. It's visible. It's not invisible. Creating new effects is just creating new data types. It's just normal Haskell. It's not anything unusual. And streaming is taken seriously. There's no reason effectful couldn't have that, but the effectful world has not adopted that as far as I know. And I think they really should. I'd very, very much recommend it. I think it's extremely useful to program that way. There are some positives from effectful. People tell me, won't you get really annoyed passing effects all the time? Don't we actually want them to be implicit? I think I personally don't, but people do think that, so I have to take that seriously. I mean, maybe that doesn't suit certain people or certain styles of programming, and I have to acknowledge that's the thing you have to do. You have to pass around these effects. You have to pass around I/O. There's an IOE effect. There can be only one. Contrary to state effects or exception effects, I don't want two IOs of the same type. There's no two IOs that I can do. I can't do one IO here and one IO here. It's just one IO. So it seems particularly strange to have to pass them around. I would never want to pass two IOs into my function. So that's a bit odd. And you do have to do that in Bluefin. Maybe a synthesis of both approaches would work better. I don't know. But at the moment, I'm just happy with the very straightforward, very sort of hands-on approach of Bluefin. Do everything manually. And it can be a bit of a pain, but equally, it's very clear and straightforward. So I like that part of the trade-off, that part of the design space. Yeah, Ollie.
I think you're missing one more sales point here as well, which I don't think you can do in effectful at all, which is it's just so lightweight to kind of get a sub-effect out of something. So if I've got like a big effect with all sorts of different methods in, and I just want to give a few methods directly to some kind of downstream code, it just feels like Bluefin is like almost made to do that, right? I can just kind of pluck out two fields out of the effect and just, in fact, I could just hand ink counter impl the downstream, right?
Yeah, you can pass any of these things.
Yeah, that top one I'd have to package up, I guess. But even that would be so easy to package kind of essentially one function into a new method and into a new effect, whereas effectful, I've got to create a new effect type, create an interpreter. Everything has to kind of be at the top level, whereas I guess Bluefin, I can just literally inline almost everything except maybe some data types. Yes,
I think it's easiest to see in the case of concrete effects like a stream or an exception. If I've got a counter in scope and I want to pass it to a function that doesn't know anything about counter but does some logging, I can just pass it this stream stringy value and it will log to that stream. So yeah, that is that's definitely a point. Great point. Thanks, Ollie.
I think the not passing things. So there's, I think there's a bit of a tension between the one of the things you like about effect systems is the fine grainedness, and that does mean that the boilerplate can get a bit out of hand. So I think it's interesting to look at some of our code. So I'm looking at a function now that has 23 effectful effects, which already is a lot of constraints. And then I don't think any of those obviously bundled together either. They're actually all doing pretty different things, and it would be unpalatable to also have 23 value level arguments, which then all had to be piped individually and not all necessarily to every subsidiary call. That would frankly really suck. So yeah, I think that there's this, it's already bad enough and it's so effectful that the fine grainedness can push in the direction of having a lot of constraints, but it would I think I would go actually insane with if I had to do the handles too. Sometimes we want handles. We do have stuff that is handle-like, but
yeah, I agree. I mean, I've never seen something with 23 constraints, but I would definitely agree. I would not want to make that 23 arguments. That sounds extremely unwieldy. So I don't have a good
I mean, you could say you could package them up, right? You can say you can package them up into data types that contain all these as fields. But I did think about this in advance, and one of the things I think about with that is actually we get quite a lot of mileage out of the fact that they're all separate, because that means GHC gives pretty good unused constraint warnings, because effectively it's a big fat record, and so if you stop using any individual bit, it will tell you, and so it's quite easy for us to stop using something and then tidy it up from everywhere that uses it. I mean, you get the same problem if you try and use constraint synonyms, that unused constraint warnings stop working so well. So that it's a little painful to have it all unpacked in some ways, but there are some nice nice effects of it.
Yeah, I can see that. I mean, you also get unused argument warnings,
right? But then you'd have to have all 23 of them rather than packaging them up together.
Yeah, that's right. Yeah, if you have 23 separate effects, I don't think Bluefin's got a good story for that. No.
I do think that the Bluefin effectful, if they had the same F monad and you could just switch between having something as a constraint carried effect and a value level effect, that would be very nice. We have such places where we basically do that manually, where we have something that is really a handle, and then we have like a little local effect for using it, and you can do a with thing to translate from the handle into the effect, and it would be really cool if that was just a native thing that worked for everything.
Well, let's have a look at this.
Is this all? I think what I'm looking at is this all using the same F monad though, or do they use different F monads?
It's using, well, this particular example is showing how to use effectful's F monad and run Bluefin operations in it. So here the type is colon greater than for effectful's containment operation. And the one with only one colon is Bluefin's one. So here I'm passing a Bluefin state handle. This is literally Bluefin state. And I'm doing the same thing where I have to pass the Bluefin constraint or to apply the Bluefin constraint also. And I just use that inside effectful by using this use Bluefin function. And everything else that's going on is effectful. So I have an effectful state, an effectful error, and I have this special type that I've defined called effectful's Bluefin. And that just says I can do Bluefin stuff with inside effectful. So I have a branch that does all of this. And the opposite as well allows you to run effectful stuff inside of Bluefin's F.
And then you just need something that generates the Bluefin version and the effectful version, and lets use both kinds of functions at the same time.
Yeah, this is a bit rough. I haven't used this in practice, and I haven't committed it into Bluefin. It is still a branch, but I think this works, and it really should work because they are just I/O. They're both just I/O. They both use the type system for assuring type safety. So possibly there's something here that means it can't work because it would violate type safety. I'm not sure, but I think this is plausible. And for people who use effectful and want to try Bluefin or vice versa, this could be a very nice way of getting started with that. And since I know you use effectful a lot in CircuitHub, if you want to experiment with Bluefin, this could be a way of getting started with that. But I haven't tried it in anger. If you'd like to, please be my guest. I'd be very interested to know how that works. So that is something that's plausible to do. And maybe we'll find down the road that having a world where you can kind of do both of these things, you can have handles and you can have constraints, and you then just choose which is the most appropriate one for your particular use case. So I'll basically conclude my talk there with these links to contact me. You're always welcome just to file an issue on the GitHub Bluefin repo to ask any questions about that. It doesn't have to be a bug report, could be a question, comment, anything at all you like, or you can always email me, and my email address is always at this webpage. So you can click on these links. I'll paste this into the chat here of the talk. But that concludes the talk. So thanks very much for allowing me to present this. I'm happy to answer more questions here now or in the future if you want to reach out to me.
Thank you for the talk. I would just say, as a relative newcomer to Haskell, I've had my fair share of very confusing type errors with effectful effects and incoherent instances. And so I think as a newbie, this seems like it might be easier to get started with. I'm curious to try it out.
Oh, great, thanks. That's definitely my experience as well. I've found the type errors that Bluefin throws up to be a lot simpler than the ones that effectful throws up. So I'm very happy with it in that regard. But I don't have that much experience with effectful either, so there may be something I'm missing. But definitely keen to see how it works out for people who are used to effectful, or, well, anyone really, how it turns out in practice for them.
I had a very basic question, Tom. So you had that with early return at some point, and you passed a ret argument. I just wanted to check what the type of ret was.
Sure. So let me present this again. So with early return is just implemented in terms of an exception. So ret here is it's going to be an exception handle that can throw an exception of type A. So when you get down here and you call return early, of maybe A, you have your maybe A here, and you throw it as an exception to the with early return, and it just says, oh, well, that's the return value now of my function. So the just X will be the return value here.
I guess I'm used to that with pattern, that argument being a function, like ret itself being a function. So I'm guessing in this case, so you return early is the function that takes ret. So I guess ret is some kind of exception type. I don't know.
Yeah, that's right. Let me actually bring up the haddocks for that. It'll probably be easier to see on there.
I guess could ret be kind of like a proxy or something?
Oh, no, it definitely couldn't be a proxy.
Oh, okay.
It does contain actual data. So with early return, here we can see a use of with early return, and we're passing in a block of code that starts by accepting the early return handle. I think Haddock doesn't do a great job of formatting this this documentation, actually, because it puts on these effects type signatures and it makes it look very complicated. It makes it look more complicated than it is. But the type of E here and the type of ret in the code we were just looking at is this thing. It's an early return RE. It means I can return early with a value of type R, and E is the effect tag that just says it belongs to this E's thing.
Okay.
So I've just been thinking about this in general and what, is there anything Bluefin can't do? And I was kind of thinking about coherence and stuff. I do think one thing that Bluefin can't do is kind of the ability to have a kind of local operation for things like reader. And the only reason that works in effectful is because that actually does mutate essentially some kind of internal state. And we do use this in some of our own kind of effect interpreters in quite a few places. We have operations like I want to introduce a new kind of client identity for like some kind of internal subsystem. And I'm not sure if Bluefin is able to.
Why wouldn't it be able to do local, given that it is functionality?
I feel any of these local things, like the local operation for a reader monad, has to be done by a new handler. I don't think you can use a common handler and have a local operation.
So you can sort of do it.
Yeah.
And the way you can sort of do it is you could define local to take this. Do you want it for a state?
Well, let's maybe look at reader, for example, because
reader's a funny one, because in Bluefin reader RE, that's just an R. Because you're passing it at a value level, it's no different from an R. It's just a new type. It's slightly easier maybe to see a.
That's why I'm like, surely you can do local. It's just that local will modify local will modify the actual like effect handle, right?
Yeah.
You know, local for reader will take the previous reader and an R to R and give you a new reader that you then pass in.
Sure. I mean, yes, if you don't do it in the context of like what local actually does. So let's to give you a concrete example. I've got an effect where I can create requests. That's like one of the operations in the effect. And whenever I create a request, it goes to the kind of current queue that I'm within. And I've got another operation within that effect, which is called with fresh queue, which takes another monadic block. And now any request that I create inside that queue gets associated to that queue. And we do that in effectful with a single effect that lives through the lifetime of the entire program, but uses this kind of local operation such that whenever I say with fresh queue, I kind of internally mutate my local state to say this is the kind of active queue that any request should be associated with. I'm maybe even more mentioning this to be like jogging my memory that I should bring this up on the Bluefin tracker, because I'm not quite sure we're going to get the subtleties here.
Well, let me write something that Bluefin can do. Let's say something like with local state. I don't know if that's a very good name for it. Maybe it should be called something like with transactional state or something. So this operation that I'm imagining defining takes a state, and it takes a stateful operation. And I'm imagining what happens is that when you invoke the stateful operation, it reads the state, this input state, and copies it to the new one, allows you to manipulate it, and at the end copies it back. And if there's an exception within here, it won't copy it back. So that's sort of transactional somehow. Now in the effectful world, or even the transformers world or whatever, it would look like just state S is in ease. Something like you map from one thing to the same thing, and you kind of implicitly pass this thing in here, and it's the same thing. So I think this is the kind of thing you're thinking about. So you can do it in Bluefin like this. And don't follow entirely your queue.
No, I think yeah, it's interesting. I think it shifts because you have to kind of, you know, that inner state that gets passed to that function there is not the same as the one that you got originally, but that's kind of the point with local state, of course. So yeah, it's interesting. You kind of have to kind of change the handler that you pass around. So yeah, maybe I take my claim that you can't do it to it's just like it's
well, it has some. I mean, it has some downsides. You if you're not careful, you can use the original state in here. That would be bad. But also, if you're not careful, you can use the original state in here. I don't think this this protects you. I think it makes it hard to do, but I don't think it stops you from doing it. So you can do this kind of thing. I think you'd have a slightly different pattern for doing it in Bluefin.
Yeah. And I guess, yeah, on that, like accidentally using the wrong thing, this is where it gets slightly difficult with, you know, GHC doesn't have a great story around. Sometimes I intentionally want to shadow a variable name, right? Like maybe within this, like with local state, I definitely don't want to touch the outside one. And I could do that by
Right.
shadowing the variable name, but then GHC starts complaining about shadowing variables. And I want to shadow this one, but I don't want to shadow all of them. So
Yep.
that could be fixed with a GHC, you know,
Yep.
chain.
Yeah, that would work.
The other thing I've got noted down here is just on the having to thread things around and it being very annoying. Would this play with implicit parameters? Like, could I put effects in implicit params?
Unfortunately, you cannot, as far as my experiments suggest. I have tried this, and there are some strange type inference issues that I don't really understand. Can't remember if it's to do with these tags being universally quantified or what, but it doesn't really seem to work. I don't fully understand why, but unfortunately it doesn't. Be interesting to reopen that. I mean, I have a branch in the repo that tries that, and if anyone's interested, they can pick it up from there. Maybe something could be made of it, but so far it doesn't work.
This is kind of a pointless comment, but I've been thinking that if Haskell had anonymous records, you could be explicit but use record wildcards to kind of smooth over the plumbing of effects around. But yeah. Unfortunately, I guess there's no way to do that without having the records and without having records everywhere for your effects.
Yeah, it's an interesting idea. I hadn't thought of that. But yes, you could bring a whole bunch of effects into scope with record wildcards and then package them up with maybe it's the same extension, I can't remember. But yes, that's quite an interesting idea. But without anonymous records or without some sort of row typing, that might not be flexible enough to be worthwhile.
I often lament that there's no such thing in Haskell. Do you know if there's any proposals to add that kind of thing?
I've seen them floating around, proposals for that, but I don't know how serious they are or how seriously they've been developed. Others on the call might have more of an idea. Not sure.
Okay, I think that's all the questions I have. I also just wanted to say thanks a lot, Tom. I feel like effects is something that I'd always kind of pushed off to the side and not thought about too much, and I actually learned quite a lot.
Oh, great!
Listening to this.
Yeah, you're welcome. You're welcome. Thanks for having me to talk.
I was thinking as well, and the kind of issue with threading things around. I think in some sense, you could think about that as a good thing, right? That it's kind of encouraging you to structure your code in a way where kind of your effectful code is separated out from your non-effectful code. And I think, you know, making it kind of painful to make things effectful can kind of be helpful to that end. Although I guess if stuff is just inherently effectful, that's not the nicest thing. But yeah, I guess you can kind of think of that as a positive as well.
I found a lot of stuff is inherently effectful, and I haven't yet got fed up with passing these arguments. Time may prove differently, but so far it's actually very easy to pass them. You generally do nothing with them. You just take them as arguments and pass them somewhere else. They can often be inferred. Type inference just tells you what they have to be. So it's very straightforward, and it leaves you with an artifact, which is some code where you can see the flow of effectful behaviors just in the surface syntax, don't need to do any type checking, type inference to see that. It's just part of the source surface syntax, which is a very nice property.
Definitely.
So there's a little bit of a caveat of the just read the source thing, which is you kind of do need to check that, again, you haven't shadowed an effect with a new handler, right? Like I could redefine my state effect, and then if I just search for state, I'm saying, oh, look, it's all here. And then I'm like, oh, wait, but this one's slightly different, which I was also wondering, it's like kind of related to, you know, you kind of have no coherence guarantee, which is kind of the point, but also I guess is maybe a little bit double-edged. Like it doesn't seem like it's a correctness issue necessarily to not have coherence between always using the same effect handler. It does complicate reading the source a little bit, I think.
Well, it's basically an analogous issue to I have two values of the same type in my program. And could it have come from one place or could it have come from another place? Generally, we're used to dealing with that. In some cases, we might think, oh, values of this type are so special because they're my sort of global state, or they're my global something or other. We only really expect to have one of them. And until now, effects have been that in the Haskell world. We've generally thought we have one of each type, and that's just the way effects are. That's the nature of effects. Bluefin's challenging that. It's saying, actually, let's try doing it a different way. We can have two or more of the same type. And that comes with all the benefits and all the drawbacks of having two or more values of the same type, of any kind of type, effects or not, in scope. That can be confusing or it can be useful, and it's up to us to make use of it in the right way.
Cool. Anyone else for any questions? Well, yeah, thanks, Tom. That was really, really cool. And that is a very cool library. So I think we might take you up on the offer of a effectful Bluefin bridge and see what we can make of that. But yeah, thank you so much.
Super. Thank you. Thanks for attending, and good to see you all.
Yeah.
See you online, and hopefully with some Bluefin collaborations.
Yeah, thank you very much, Tom.
See you later, guys.
Thanks, Tom.
See ya.